The morning fog clung to the concrete runways of Ford Motor Company's Willow Run bomber plant as the 6,500th Consolidated B-24 Liberator rolled off the assembly line on April 24, 1944. The massive four-engine bomber, her aluminum skin gleaming under the Michigan sun, represented something unprecedented in the history of warfare. Industrial might converted into strategic striking power at a scale the world had never witnessed. Charles Sorensen, Ford's production chief, watched from the observation deck as another B-24 emerged from the mile-long assembly line exactly 59 minutes later. Behind him, the statistics board displayed numbers that would have seemed impossible just 3 years earlier. 8,685 Liberators manufactured at Willow Run alone, with 42,000 workers operating in 2 9-hour shifts, 7 days a week. The plant consumed 3.5 million square feet of factory space, making it the largest enclosed room on Earth. But these were not merely statistics on a production board. Each of those bombers carried within its aluminum frame the capacity to close what Allied strategists called the Atlantic Gap, that deadly stretch of ocean beyond the reach of land-based aircraft where German U-boats hunted Allied convoys with near impunity. The B-24 Liberator, with its innovative Davis wing and operational range of 2,400 miles, would prove to be the weapon that finally turned the tide in the Battle of the Atlantic. The story of how America's most produced bomber became the maritime patrol aircraft that crushed the U-boat threat begins not in the skies over the North Atlantic, but in the engineering offices of Consolidated Aircraft in San Diego, California, where designer David R. Davis had created a wing profile so efficient that California Institute of Technology engineers initially hesitated to report their wind tunnel results. The wing showed efficiency that exceeded what was thought possible, outperforming contemporary designs by 20%. December 29, 1939 marked the first flight of the XB-24 prototype, but few could have predicted that this angular, slab-sided bomber would become the most decisive anti-submarine weapon of World War II. The aircraft that ground crews would nickname the Flying Boxcar possessed characteristics that made it ideally suited for long-range maritime patrol. Unprecedented endurance, spacious bomb bays that could accommodate fuel tanks for extended range, and a stable platform for the radar and searchlight equipment that would revolutionize anti-submarine warfare. The Royal Air Force recognized these capabilities first. When France fell in June 1940, the British took over French orders for 139 LB-30 variants, immediately designating them as Liberator GR-1s for general reconnaissance duties with our AF Coastal Command. These early maritime patrol aircraft, stripped of armor and defensive armament to save weight, carried additional aviation gasoline in their bomb bay tanks and were fitted with ASV Mark II radar air-to-surface vessel detection equipment that could spot a surface submarine at ranges up to 14 miles. Wing Commander Humphrey DeVerd Lee, and our AF personnel officer with no formal engineering training, would create the innovation that transformed these radar-equipped aircraft into deadly submarine hunters. Chatting with returning air crews in the officers' mess at our AF bases across Britain, Lee learned of a critical tactical problem. ASV radar had a minimum detection range too long for visual contact at night. Aircraft would detect a submarine on radar, approach the target, then lose it in the radar's blind spot at the exact moment when visual acquisition was most crucial. The solution Lee devised was elegant in its simplicity. Mount a powerful searchlight under the aircraft, pointed forward, allowing the submarine to be spotted the instant the light was activated. Working in secret and without official sanction, Lee developed what would become known as the Lee Light, a 22 million candela carbon arc searchlight 24 inches in diameter. The Air Ministry remained unaware of the project until Lee demonstrated the completed prototype. In March 1941, a Vickers Wellington DWI that had previously been used for magnetic minesweeping operations was modified with a retractable dustbin, holding the lamp. The aircraft already possessed the necessary generator, making it an ideal test platform. The concept proved sound immediately. By June 1942, aircraft equipped with ASV radar and Lee lights were operating over the Bay of Biscay, intercepting U-boats moving between their combat patrol areas and home ports along the French coast. The first submarine successfully sighted was the Italian submarine Torelli on the night of June 3, 1942. The first confirmed kill came just over a month later when U-502 was sunk on July 5, 1942. The combination of radar detection and searchlight illumination proved so effective that German submarine crews were forced to reverse their operational patterns entirely. For generations, submarines had surfaced at night to recharge their batteries in relative safety. Now, U-boat commanders ordered their vessels to remain submerged during darkness and surface only during daylight hours when they could at least see attacking aircraft approaching. Captain Lieutenant Klaus Rudloff of U-609 understood the mathematics of submarine warfare better than most. In the cramped control room of his Type 7C U-boat, 48 meters long and displacing 769 tons, Rudloff had calculated the precise timing required for a crash dive, 35 seconds from the moment lookouts spotted an approaching aircraft until the submarine's hull cleared the surface. The appearance of radar-equipped liberators changed those calculations fundamentally. On the night of August 15, 1942, patrolling 60 nautical miles west of Brest, Rudloff's boat was caught on the surface by a Liberator of No. 120 Squadron RAF. The aircraft's ASV Mark II radar detected U-609 at a range of 12 miles. The U-boat's METOX radar warning receiver provided only 18 seconds of advance warning before the lee light burst from the darkness, turning night into day with an intensity of 22 million candle power. Rudloff's after-action report, filed upon his return to the submarine pens at Lorient, described the encounter with clinical precision. Enemy aircraft approached from bearing 270 at altitude estimated 100 meters. Radar detection alarm sounded at 23:42 hours. Crash dive ordered immediately. At 23:43 hours, searchlight illumination from bearing 285 revealed our position completely. 6 depth charges detonated in close proximity during dive sequence. Hull damage to frames 62 through 68. Forward torpedo room flooded partially. U-609 survived that encounter, but Rudloff's report joined hundreds of similar accounts flowing into the headquarters of Befehlshaber der Unterseeboot, commander of submarines, where Gross Admiral Karl Donitz watched his carefully calculated tonnage war slip beyond his control. The mathematics that had once favored the U-boats now worked against them. Before the introduction of radar-equipped liberators, a surface submarine had approximately 4 minutes to detect, evaluate, and dive beneath an approaching aircraft. With radar and lee lights, that margin shrank to less than 30 seconds. The technical specifications of the Liberator maritime patrol variants told the story of this tactical revolution. The aircraft carried depth charges weighing 250 pounds each, or larger 600-pound charges designed specifically for anti-submarine warfare. The Mark 24 mine, actually an acoustic homing torpedo, gave Liberator crews their most deadly weapon against submerged U-boats. Though classified as a mine for security purposes, this weapon actively hunted submarines using acoustic guidance, achieving a kill rate that far exceeded conventional depth charges. Lieutenant Heinrich Zimmermann, commander of U-136, experienced the deadly effectiveness of these new weapons during a patrol off the coast of Morocco in November 1942. His war diary, recovered after the boat's sinking, recorded the final engagement. Liberator aircraft detected on radar bearing 110, range 8,000 meters. Crash dive initiated. At depth 15 meters, acoustic torpedo impact amidships between frames 41 and 45. Flooding uncontrolled in engine room and aft torpedo compartment. Boat sinking rapidly. The acoustic torpedo that killed U-136 was one of thousands manufactured at the Western Electric Plant in Burlington, North Carolina, where assembly line workers who had never seen a submarine built the weapons that would sink them. Each Mark 24 mine weighed 680 pounds, carried a 92-pound warhead, and could home on submarine propeller noise at ranges up to 4 miles. Between 1943 and 1945, these weapons sank 37 Axis submarines. The industrial miracle that made such weapons deployment possible reached its peak at Ford Motor Company's Willow Run facility, where the marriage of automotive mass production techniques with aircraft manufacturing created what journalists called the eighth wonder of the world. The statistics of production at Willow Run transcended mere numbers to become a strategic weapon in their own right. Albert Kahn, the architect who designed the facility, created a building so large it threatened to extend into 2 Michigan counties. To avoid paying taxes in both jurisdictions, Ford turned the assembly line 90 degrees, approximately 2/3 along its length, installing massive turntables that rotated partially assembled liberators so production could continue without interruption. Workers dubbed these mechanisms the tax turns. The human dimension of this production miracle encompassed more than statistics. Mary Parker, a riveter from Tennessee who joined the Willow Run workforce in February 1943, operated pneumatic rivet guns that drove aluminum fasteners into the aircraft's frame at precisely calculated intervals. Her daily quota, 420 rivets driven with mechanical precision. Across the factory floor, workers like Parker installed 360,000 rivets in 550 different sizes to complete each B-24. The training program at Willow Run resembled a military operation in its scope and efficiency. The Aircraft Apprentice School processed up to 8,000 students per week, transforming workers with no previous aircraft experience into skilled technicians capable of manufacturing one of the most complex machines of the war. Mock UPS constructed from plywood allowed students to practice installing components before working on actual aircraft. The dormitory complex adjacent to the factory housed 1,300 aircrews who slept in cots while waiting for their aircraft to emerge from the assembly line. These men would fly the bombers directly from the factory to operational bases around the world, but their temporary quarters at Willow Run gave them an intimate understanding of the industrial effort behind their weapons. Captain Robert Chen, a B-24 pilot who picked up his aircraft at Willow Run in March 1944, described the experience in a letter to his wife. The factory extends as far as you can see in both directions. There are liberators everywhere, some just frameworks of aluminum tubing, others nearly complete with engines installed and propellers attached. The noise is constant, a symphony of riveting guns, hydraulic presses, and electric motors. These workers are building the tools that will win this war, and they know it. By December 1944, Willow Run had achieved production rates that exceeded the capacity of the military to absorb the aircraft. Brand new B-24MS rolled directly from the assembly line to reclamation sites where they were scrapped for aluminum before ever entering combat service. The war in Europe was ending, and strategic bombing in the Pacific had transitioned to the longer-ranged B-29 Superfortress. The transformation of the B-24 from strategic bomber to submarine hunter required technological innovations that pushed the boundaries of 1940s electronics. The ASV Mark II radar system, developed by British scientists working under the pressure of the Battle of Britain, represented a quantum leap in maritime surveillance capability. The radar's transmitter generated pulses of radio energy at a wavelength of 1.5 meters, broadcasting at a power level of 7 kilowatts. These pulses bounced off surface targets and returned to the aircraft's receiver, where they appeared as bright spots on a cathode ray tube display. The range against a surface submarine averaged 8 miles in good conditions, extending to 12 miles under optimal atmospheric circumstances. Squadron leader James Morrison, a radar operator with No. 220 Squadron RAF, became one of the first specialists trained on the ASV Mark II system during its operational introduction in late 1941. His logbook recorded the technical challenges of operating electronic equipment in the harsh environment of maritime patrol aircraft. Radar serviceable for 6 hours continuous operation before tube failure. Replacement required every fourth sortie on average. Range accuracy plus or minus 500 yards at 8-mile detection range. Aircraft altitude must remain below 2,000 feet for reliable surface detection. The radar's limitations drove tactical innovations that would define anti-submarine warfare for the remainder of the conflict. The system's minimum detection range created a dead zone, extending from the aircraft to approximately 1 mile ahead. Once an aircraft began its attack run, the submarine disappeared from radar coverage at precisely the moment when accurate navigation became most critical. This technical constraint led directly to the development of the Lee light and the attack procedures that made radar-guided submarine hunting possible. The display system consisted of 2 cathode ray tubes, a main 6-inch tube for general scanning and a smaller 3-inch height scope, used for altitude measurement and coordination with navigation aids. The height scope also served as a timing mechanism for Lee light illumination, allowing radar operators to coordinate searchlight activation with the final attack approach. Technical Sergeant William Rodriguez, an ASV radar specialist with the United States Army Air Force's Anti-Submarine Command, trained on similar equipment at the Massachusetts Institute of Technology's Radiation Laboratory before deploying to operational squadrons in 1943. His technical manual, preserved in the National Archives, detailed the precise procedures for submarine detection. Initial sweep from bearing 000 to bearing 180 degrees. Sweep rate 4 revolutions per minute. Gain control set to position 7 for initial detection. Reduced to position 4 for final approach. Range scale selection dependent on tactical situation. 8-mile scale for general patrol, 2-mile scale for attack phase. The introduction of ASV Mark III radar in March 1943 represented the next technological leap in submarine detection. Operating on a wavelength of 10 centimeters instead of 1.5 meters, the new system provided dramatically improved range and accuracy while reducing the effectiveness of German radar warning receivers. The shorter wavelength allowed for more precise target definition, enabling operators to distinguish between submarines and surface vessels, or even to detect a submarine's conning tower when the hull remained submerged. The technical specifications of ASV Mark III radar reflected advanced engineering far beyond the capabilities of most 1940s electronics. Transmitter power increased to 100 kilowatts, detection range extended to 20 miles against large surface targets, and resolution improved to 50 yards at maximum range. The magnetron technology that made these improvements possible had been developed as part of the British Cavity Magnetron Research Program and shared with American scientists through the TIZARD mission in September 1940. Dr. Edward Mitchell, a physicist who worked on radar development at the Bell Telephone Laboratories during the war, later wrote of the technological challenges involved in adapting land-based radar systems for maritime patrol aircraft. The aircraft environment presented problems we had never encountered in fixed installations. Vibration, temperature variation, electrical interference from engine ignition systems, and space limitations required complete redesign of every component. The ASV Mark III represented not merely an improvement in existing technology, but a fundamental advance in miniaturized electronics. The German response to these radar developments demonstrated the technological arms race that characterized electronic warfare throughout the conflict. The METOX radar warning receiver, introduced in August 1942, allowed U-boat crews to detect ASV radar emissions at ranges greater than the radar's own detection capability. This early warning system provided submarine commanders with sufficient time to dive before aircraft could achieve visual contact. Captain Lieutenant Horst Degen of U-701 described the tactical advantage provided by METOX in his patrol report from September 1942. Radar detection alarms sounded at range estimated 15 kilometers. Crash dive completed before enemy aircraft achieved visual contact. 3 depth charge attacks over 15-minute period failed to achieve damage to boat. METOX receiver provided tactical advantage sufficient to avoid destruction. However, the Allied introduction of centimetric radar rendered METOX obsolete almost immediately. The German radar warning receiver operated on frequencies designed to detect 1.5-meter wavelength transmissions. When ASV Mark III began operating on 10-centimeter wavelengths, existing German warning systems could not detect the new signals. U-boats once again became vulnerable to surprise attack. The German technological response came in the form of the Naxos radar warning receiver, capable of detecting centimetric radar emissions. But by the time Naxos entered service in sufficient quantities, the U-boat force had already sustained losses that crippled its operational effectiveness. The window of technological advantage had shifted decisively to the Allies. Captain Saburo Sakai of the Imperial Japanese Navy's 251st Air Group understood the tactical challenge posed by American B-24 Liberators better than most fighter pilots in the Pacific Theater. From his base at Rabaul, New Britain, Sakai had encountered Liberators of the United States Army Air Force's 5th and 13th Air Forces on multiple occasions between 1943 and 1944, each engagement teaching him more about the bomber's defensive capabilities and operational limitations. The technical specifications of the B-24J variant that dominated Pacific operations included 10 Browning M2.50 caliber machine guns arranged in 6 defensive positions: nose, tail, top turret, ball turret, and 2 waist positions. Each gun fired 850 rounds per minute, creating a defensive envelope that could engage attacking fighters from virtually any angle. The .50 caliber ammunition, weighing 45 grams per round, could penetrate aircraft armor at ranges exceeding 1,000 meters. Sakai's encounter with liberators of the 43rd Bombardment Group on April 7, 1944, demonstrated both the bomber's vulnerabilities and its remarkable defensive firepower. His combat report, filed with 5th Fleet Headquarters, recorded the engagement in precise detail. Enemy formation consisted of 12 B-24 aircraft at altitude 6,000 meters, proceeding northwest toward Wewak. Initial attack from port quarter high angle. Defensive fire commenced at range 800 meters. Number 2 aircraft in formation suffered engine fire after concentrated attack. Broke off engagement after sustaining damage to starboard wing and engine cooling system. The B-24 that Sakai damaged managed to return to its base at Nadzab, New Guinea, despite severe battle damage. This incident illustrated the bomber's reputation for absorbing punishment and surviving encounters that would destroy less robust aircraft. However, the same engagement also revealed tactical weaknesses that experienced Japanese fighter pilots learned to exploit. Lieutenant Colonel Yasuo Ichikawa, commanding officer of the 68th Sentai Flying Kawasaki Ki-61 Tony fighters, developed tactics specifically designed to counter B-24 formations during the spring of 1944. His tactical manual, distributed to fighter units throughout the Southwest Pacific, outlined the preferred attack methods. Approach from directly ahead at same altitude, close to range 200 meters before opening fire. Concentrate fire on cockpit area and forward fuel tanks. Break downward immediately after attack to avoid defensive crossfire from formation. These head-on attacks exploited the B-24's most significant defensive weakness, the nose turret's limited field of fire. Early production B-24s relied on single manually operated guns in the nose position, providing inadequate protection against frontal attacks. Later variants incorporated powered nose turrets, but the improvement came too late to affect most Pacific theater engagements. Staff Sergeant Owen J. Baggett of the 7th Bombardment Group experienced Japanese fighter tactics from the receiving end during a mission to attack railroad bridges near Pyongyang, Burma, on March 31, 1943. Baggett's B-24D Blue Dream came under attack from Nakajima Ki-43 Oscar fighters, approximately 60 miles from the target. His account of the engagement, recorded in his post-war memoir, provided insight into both the intensity of Pacific air combat and the personal courage required of bomber crews. The Oscars came at us from every direction at once. I was in the waist gunner position, firing at a fighter coming up from below when I felt the aircraft shudder and heard Lieutenant Peterson yell, "Fire in number 3 engine." The bomber started losing altitude immediately. Peterson gave the order to bail out when it became clear we couldn't maintain level flight. Baggett's parachute descent became the setting for one of the most remarkable individual combat actions of the Pacific War. Japanese fighters continued attacking the American crew members as they descended, killing 2 men and wounding Baggett in the left arm. Feigning death while hanging in his parachute harness, Baggett waited as a curious Oscar pilot approached to within pistol range. Drawing his service sidearm, a Colt .45 caliber Model 1911 A1, Baggett fired 4 rounds, hitting the Japanese pilot in the head and causing the fighter to crash. The technical impossibility of this engagement, firing a handgun accurately while suspended from a parachute, made Baggett's account controversial among aviation historians until Japanese records confirmed both the fighter's loss and the circumstances of the pilot's death. Warrant Officer Kazuo Takatsuka had indeed been killed by small arms fire during the engagement, and his aircraft had crashed in the location Baggett described. Upon capture, Baggett was taken to a prisoner of war camp where the Japanese commanding officer, Colonel Hiroshi Suzuki, praised his marksmanship as an example of warrior spirit worthy of respect. This incident illustrated the complex honor code that sometimes governed Japanese military behavior, even toward enemies. The broader tactical implications of Pacific Theater B-24 operations extended far beyond individual combat actions. The bomber's extraordinary range, 2,850 miles with a 5,000-pound bomb load, allowed American forces to strike targets previously beyond the reach of land-based aircraft. The November 15, 1944 raid on the Omura Aircraft Factory in Kyushu marked the first time B-24s had bombed the Japanese home islands from bases in China. Major James Chen, operations officer for the 308th Bombardment Group stationed at Chengdu, China, calculated the logistics required for these extreme-range missions. Round-trip distance to Omura, 2,200 miles. Fuel consumption, 290 gallons per hour average. Total fuel required, 1,600 gallons. Maximum fuel capacity with bomb bay tanks, 3,614 gallons. Operational margin, sufficient for 15 minutes over target, plus 1 hour reserve. These calculations revealed both the B-24's capabilities and its limitations in Pacific operations. The distances involved in Pacific theater missions pushed the bomber to its absolute range limits, requiring careful fuel management and perfect navigation. Weather conditions, headwinds, or mechanical problems could easily transform a successful mission into a disaster. The human cost of these extended-range operations appeared in casualty statistics that told a sobering story. Of the 240 B-24s assigned to the 20th Bomber Command's China-based operations, 93 were lost to all causes between June 1944 and January 1945. Enemy action accounted for only 22 of these losses. The remainder resulted from mechanical failure, weather, navigation errors, or fuel exhaustion over the vast expanses of the Pacific Ocean. Maggiore Vittorio Minguzzi commanded the 359th Squadriglia of the 22nd Gruppo Caccia when American B-24 Liberators first appeared over Naples in January 1943. From his base at Capua, north of the city, Minguzzi watched the angular, twin-tailed bombers approach in tight defensive formations that seemed impervious to conventional fighter attack. His unit, equipped with 8 French-built D-Voitin D-520 fighters acquired after the armistice with France, represented one of the Regia Aeronautica's last effective interceptor squadrons. The technical specifications of the D-520 revealed both its capabilities and limitations when engaging American heavy bombers. Maximum speed of 535 km per hour at altitude gave the Italian fighters a significant speed advantage over the Liberators, but the aircraft's armament 120mm Hispano-Suiza HS-404 cannon and 4 7.5mm MAC machine guns proved marginally effective against the B-24's robust construction and defensive armament. Minguzzi's first engagement with B-24s occurred on March 1, 1943, when 12 Liberators of the 98th Bombardment Group approached Naples at an altitude of 7,000 meters. His combat report, filed with the 5th Squadra Area Headquarters, described the tactical challenges of attacking American heavy bomber formations. Enemy aircraft maintained tight defensive box formation throughout approach. Initial attack from Port Quarter High resulted in intensive crossfire from multiple defensive positions. Concentrated fire on lead bomber's starboard engines produced visible damage and smoke trail. Aircraft maintained formation discipline despite battle damage. The B-24 that Minguzzi damaged that morning managed to drop its bombs on the Naples harbor complex before attempting to return to its base at Amendola. The bomber, piloted by First Lieutenant Robert Morrison of the 414th Bombardment Squadron, struggled to maintain altitude with its No. 3 engine feathered and significant damage to the starboard wing. Morrison's crew threw out everything not essential for flight: ammunition, emergency equipment, personal belongings, in a desperate attempt to reduce weight. The damaged Liberator finally crashed into the Mediterranean 40 miles southeast of Naples, but not before Morrison had maintained formation discipline long enough to complete the bomb run. 7 of the 11 crew members survived the water landing and were rescued by Italian naval forces. This incident typified the ruggedness that made the B-24 both respected and feared by Axis fighter pilots throughout the Mediterranean theater. Colonel Giuseppe Santini, commanding the 4th Stormo Caccia based in Sicily, developed specialized tactics for engaging B-24 formations during the intense air battles of summer 1943. His tactical manual, issued to Italian fighter units in July 1943, outlined the preferred methods for attacking American heavy bombers. Approach from high-altitude advantage. Concentrate multiple aircraft against single bomber from different angles simultaneously. Target engines and fuel systems rather than attempting to kill aircrew. Break off engagement immediately after single pass to avoid prolonged defensive fire. These tactics reflected hard-won experience against American bomber formations that had been decimated Italian air defenses throughout the spring of 1943. The numerical superiority of American formations, combined with their defensive firepower and ability to absorb battle damage, made traditional Italian fighter tactics obsolete. Single aircraft attacks had proven suicidal. Only coordinated multi-aircraft assaults showed any prospect of success. The technological disparity between Italian and American aircraft became increasingly apparent as the Mediterranean campaign progressed. B-24s carried advanced Norden bomb sights that allowed accurate bombing from altitudes beyond the effective ceiling of most Italian fighters. The bombers' turbocharged engines maintained full power at altitudes where Italian aircraft suffered severe performance degradation. Capitano Alberto Morelli, a veteran pilot with the 150th Gruppo flying Macchi MC-202 Folgore fighters, experienced this technological gap firsthand during an engagement with B-24s near Rome on July 19, 1943. His aircraft, powered by a German-built Daimler-Benz DB601 engine, reached its service ceiling at approximately 11,000 meters. The American bombers were operating at 12,000 meters, effectively immune to interception by aircraft that could barely maintain level flight at that altitude. Morelli's combat report illustrated the frustration felt by Italian pilots facing technologically superior opponents. Enemy formation maintained altitude beyond effective engagement envelope for Italian fighters. Attempted intercept resulted in stall condition at maximum service ceiling, unable to achieve firing position before American escort fighters intervened. P-38 Lightning aircraft engaged from superior altitude and speed advantage, forced to break off without engaging primary targets. The introduction of American escort fighters, initially Lockheed P-38 Lightnings, later Republic P-47 Thunderbolts and North American P-51 Mustangs, effectively ended Italian fighter operations against B-24 formations. The escort aircraft possessed performance advantages that made interception attempts futile. Italian pilots found themselves outgunned, outnumbered, and fighting with obsolete equipment against opponents who enjoyed every possible advantage. Lieutenant Aldo Ferrarese of the 23rd Gruppo Caccia recorded the final phase of Italian resistance in his diary entries from September 1943. Our aircraft are no match for the Americans. The D-520s are fast enough to catch the bombers, but the escort fighters destroy us before we can engage. The MC-202s cannot reach bombing altitude. The few remaining G-55s and MC-205s are too few to make any difference. We are fighting a war we cannot win with weapons we cannot replace. The Italian surrender on September 8, 1943, ended effective Axis resistance to B-24 operations in the central Mediterranean. The remaining German units, primarily equipped with Messerschmitt Bf-109 and Focke-Wulf 190 fighters, continued to contest Allied air superiority until the end of the war, but never regained the ability to seriously threaten American bomber operations. The technical development of the Lee Light represented one of World War II's most significant innovations in anti-submarine warfare, transforming night operations from blind searches into precisely coordinated attacks. The engineering challenges involved in mounting a 24-inch searchlight beneath a combat aircraft while maintaining aerodynamic stability and structural integrity required solutions that pushed 1940s technology to its limits. Two distinct mounting systems entered operational service, each designed for specific aircraft types and operational requirements. The turret type, fitted primarily to Vickers Wellington bombers, featured a retractable underturret controlled by hydraulic motors and rams. The installation weighed 1,100 pounds complete with power systems and ammunition, creating significant changes in the aircraft's center of gravity that required careful calculation to maintain flight characteristics. Technical specifications of the turret-mounted system included maximum beam intensity of 50 million candelas without the spreading lens, reduced to approximately 20 million candelas when the lens was installed for broader illumination coverage. The hydraulic system operated at 1,000 pounds per square inch, providing sufficient power to extend or retract the turret assembly in 15 seconds under normal flight conditions. The nacelle-type installation, designed for Consolidated Catalinus and B-24 Liberators, mounted a 20-inch searchlight in a streamlined nacelle 32 inches in diameter. The complete installation hung from bomb attachment points beneath the wing, connected to the aircraft's electrical system through armored cables. This design weighed 870 pounds and provided maximum beam intensity of 90 million candelas without the spreading lens. Flight Lieutenant Jeffrey Harrison, a Wellington pilot with No. 172 Squadron RAF, participated in the operational testing of turret-mounted Lee light systems during the spring of 1943. His technical evaluation report, preserved in Royal Air Force archives, documented the performance characteristics and operational limitations of the new equipment. Lee light operation requires coordination between pilot, navigator, and radar operator with precision timing critical to mission success. Light activation must occur at precisely calculated moment to provide maximum illumination during submarine attack run while maintaining aircraft safety margins. The tactical procedures for Lee light attacks evolved through trial and error during the early months of 1943, with each engagement teaching British aircrews more about the optimal methods for combining radar detection, navigation, and searchlight illumination. The standard attack profile required the aircraft to approach the submarine contact at an altitude of 500 feet, maintaining airspeed of 160 miles per hour throughout the final attack phase. Radar contact procedures called for the aircraft to begin its attack run when the submarine appeared at maximum detection range, typically 8 to 12 miles depending on atmospheric conditions and sea state. The pilot would fly directly toward the radar contact while the navigator calculated wind drift and approach angle. The radar operator monitored target movement and provided course corrections until the contact disappeared in the radar's minimum range dead zone. At this critical moment, with the submarine invisible to both radar and visual observation, the success of the attack depended entirely on precise navigation and timing. The navigator would count down the seconds until searchlight activation. Light on in 5, 4, 3, 2, 1. Light on. The Lee light would burst into brilliance, illuminating a circle of ocean approximately 400 yards in diameter with the intensity of artificial daylight. Squadron Leader Michael Thompson, commanding officer of No. 248 Squadron RAF, developed the standard operating procedures that became doctrine for all Lee light operations. His tactical manual, distributed to coastal command units in May 1943, specified the precise timing required for successful attacks. From radar contact loss to light activation, 30 seconds average flight time. Light activation to weapon release, maximum 8 seconds to achieve surprise. Total illuminated attack phase, maximum 15 seconds before submarine dive capability compromised. The psychological impact on German U-boat crews subjected to Lee light attacks proved as significant as the physical damage inflicted by depth charges and acoustic torpedoes. Oberleutnant Zur C. Werner Hartmann, commander of U-441, described the experience in his war diary after surviving a Lee light attack on September 14, 1943. Radar warning at 23:35 hours local time. Crash dive ordered immediately. At depth 8 meters, searchlight illumination turned night to day. Intensity so brilliant that water surface appeared transparent. 6 depth charges detonated in close proximity during descent. Psychological effect on crew severe. Several men required medical attention for combat stress reaction. The German response to Lee light tactics involved both technical countermeasures and changes in operational procedures. Improved radar warning receivers provided earlier detection of approaching aircraft, while additional anti-aircraft armament allowed some U-boats to remain surfaced and fight rather than diving. The policy of surface engagement, ordered by Admiral Donitz in May 1943, led to fierce gun battles between submarines and aircraft that often resulted in casualties on both sides. U-boat construction incorporated heavier anti-aircraft armament specifically to counter Lee light attacks. The Type 7 C-41 variant mounted twin 20mm flak 30 cannons in addition to the standard 88mm deck gun, while some boats received quad-mounted 20mm installations that could maintain heavy fire against low-flying aircraft. These defensive measures achieved limited success, shooting down several Lee light-equipped aircraft during the summer of 1943. However, the fundamental tactical advantage remained with the aircraft. A surface submarine presented a stationary target illuminated by searchlight, while the attacking aircraft approached at high speed from an unpredictable direction. The submarine's anti-aircraft guns could fire only in limited arcs, and the brief duration of Lee light attacks, typically less than 30 seconds from illumination to weapon impact, provided minimal time for effective defensive fire. The technical evolution of Lee light equipment continued throughout the war, with improved carbon arc systems providing greater reliability and longer operational life. Later installations incorporated automatic activation systems that eliminated the critical timing requirements of manual operation. Pilots could select automatic mode during the approach phase, allowing the light to activate automatically when the aircraft reached a predetermined range from the target. Manufacturing of Lee light equipment expanded beyond the original Savage and Parsons facility to include production lines in Canada and the United States. American-built installations equipped most of the PB-4Y Liberators that closed the Atlantic Gap during 1943 and 1944. The standardization of mounting systems and electrical interfaces allowed rapid installation of lights on aircraft being converted from bombing to maritime patrol roles. Corvette and Captain Reinhard Hartigan commanded U-123 during some of the most successful U-boat operations off the American East Coast in early 1942. But his experiences during Operation Drumbeat, the initial submarine offensive against American shipping, would be among the last easy victories for German submarine forces. By late 1942, the tactical situation had reversed completely, with U-boats becoming the hunted rather than the hunters. Hartigan's war diary from his 5th patrol, conducted between October and December 1942, recorded the changing nature of submarine warfare in meticulous detail. The appearance of radar-equipped aircraft had transformed what was once a submarine sanctuary, the surface of the ocean at night, into a killing field where death could arrive without warning from the darkness above. November 23, 1942, Hartigan wrote, "Position 47 degrees 30 minutes north, 12 degrees 45 minutes west. Surfaced at 22:15 hours to charge batteries. Radar warning receiver activated at 22:37 hours. Aircraft bearing approximately 090 degrees. Range unknown. Crash dive ordered immediately. Depth charges detonated during descent phase. No damage to boat. This marks the 15th radar contact in 12 days of patrol. Surface time now limited to absolute minimum required for battery charging." The technical specifications of Type 7C submarines like U-123 revealed the constraints that made surface detection so dangerous. The boat's electric motors could propel it at 7 knots submerged for 1 hour before battery depletion, or 4 knots for 40 hours. Surface diesel engines were required to recharge these batteries, a process that typically took 8 to 10 hours per cycle. During this vulnerable period, the submarine was effectively stationary, unable to dive quickly while maintaining electrical connections to the charging system. The introduction of Lee light-equipped aircraft eliminated even this limited surface time. Captain Lieutenant Johann Mohr of U-124 experienced the deadly effectiveness of these new tactics on March 13, 1943, during what would become his final patrol. His radio message to U-boat headquarters, transmitted just before his boat's destruction, provided insight into the hopeless tactical situation facing German submarine commanders. Aircraft attack commenced 23:45 hours. Searchlight illumination prevented evasive action. Multiple depth charge attacks. Hull integrity compromised. Unable to dive. Position 43 degrees 22 minutes north. 18 degrees 14 minutes west. Abandoning boat. U-124 and all 49 crew members were lost in this engagement, joining hundreds of other U-boats that fell victim to the expanding Allied anti-submarine campaign. The statistical analysis compiled by German naval headquarters revealed the mathematical impossibility of continuing submarine operations under these conditions. In March 1943 alone, German submarines sank 476,000 tons of Allied shipping while losing 15 boats. By May, the equation had reversed. 12 boats lost for only 264,000 tons sunk. Fregating Captain Gunter Hessler, Admiral Donit's son-in-law and chief analyst for submarine operations, calculated the precise moment when the Battle of the Atlantic shifted decisively against Germany. His classified report, submitted to Naval High Command on June 15, 1943, contained conclusions that would prove prophetic. Current loss rates make submarine campaign mathematically unsustainable. Average patrol duration has decreased from 45 days to 18 days due to aircraft interference. Tonnage sunk per boat per patrol has declined from 8,000 tons to 3,000 tons. At current rate of attrition, submarine force will be combat ineffective by December 1943. The human cost of these statistics appeared in the personal accounts of U-boat commanders who survived the worst period of the Battle of the Atlantic. Oberleutnant Zur See Klaus Barkston commanded U-521 during 3 patrols between January and August 1943, experiences that left him with profound respect for Allied anti-submarine capabilities and little confidence in German technological countermeasures. Barkston's patrol report from his second voyage described an encounter with multiple radar-equipped aircraft that illustrated the hopeless tactical situation facing U-boat crews. Patrol Day 17. Position 42 degrees 15 minutes north, 41 degrees 30 minutes west. Aircraft contacts at intervals of 2 to 4 hours throughout daylight period. Forced to remain submerged for 14 consecutive hours. Battery charge insufficient for normal operations. Surfaced at 21:30 hours to charge batteries. Radar contact at 21:42 hours. Crash dive initiated. Depth charges exploded during descent. Surfaced again at 23:15 hours. Radar contact at 23:28 hours. Pattern repeated throughout night. Total surface time, 47 minutes. Battery charge, insufficient. This patrol pattern became typical for German submarines operating in areas where Allied air coverage had achieved saturation levels. U-boats found themselves trapped between the need to surface for battery charging and the certainty of detection by radar-equipped aircraft. The mathematical progression was inexorable. Insufficient battery charge led to longer surface exposure, which increased detection probability, which led to more frequent diving, which depleted batteries faster. The German response to these tactical problems included both technological innovation and desperate tactical adaptations. The Schnorkel underwater breathing apparatus, developed by Dutch engineers before the war, allowed submarines to operate their diesel engines while submerged at periscope depth. This technology theoretically eliminated the need for surface operations, but practical implementation revealed significant limitations. U-264, one of the first boats equipped with Schnorkel apparatus, conducted trials in the Baltic Sea during February 1944 under the command of Captain Lieutenant Hartmut Lux. His technical evaluation report documented both the advantages and severe drawbacks of underwater operations. Schnorkel permits diesel engine operation at depths up to 15 meters, battery charging possible without surface exposure. However, sea conditions above force 3 cause repeated flooding of air intake valve. Diesel engine operation creates carbon monoxide hazard in enclosed compartments. Periscope depth operations required for Schnorkel use make boat vulnerable to surface vessel detection. More significantly, Schnorkel-equipped submarines could achieve speeds of only 6 knots while charging batteries, compared to 17 knots surface speed for conventional operations. This speed reduction made it impossible for submarines to maintain contact with convoy targets, effectively ending their role as offensive weapons. The technology that promised to restore German submarine effectiveness actually transformed U-boats from hunters into purely defensive weapons concerned primarily with survival. The final phase of the U-boat campaign devolved into what German submariners called the milk run. Patrols conducted primarily to maintain the illusion of offensive capability while achieving minimal tactical results. Captain Lieutenant Adalbert Schnee, one of Germany's most successful submarine commanders with 23 ships sunk totaling 119,000 tons, described the futility of late war patrols in his post-war memoir. By 1944, we were no longer hunting enemy shipping. We were simply trying to survive long enough to return to port. The ocean had become Allied territory. We were trespassers who might be discovered and destroyed at any moment. The statistical record of U-boat operations after May 1943 confirmed Schnee's assessment. German submarines sank increasingly small numbers of Allied merchant vessels while suffering catastrophic losses to Allied anti-submarine forces. In the 6 months between July and December 1943, U-boats managed to sink only 196 Allied ships while losing 131 submarines. The ratio of tonnage sunk to submarines lost had declined to levels that made continued operations strategically meaningless. The United States Navy's adoption of the B-24 Liberator as a maritime patrol aircraft created one of World War II's most effective anti-submarine and anti-shipping weapons, designated PB-4Y1. These naval variants combine the bomber's extraordinary range with specialized equipment designed specifically for over-water operations. The technical modifications that transformed Army Air Force's bombers into Navy patrol aircraft reflected the unique requirements of Pacific theater warfare. Lieutenant Commander James Patterson, commanding officer of Patrol Squadron 53, VPB-53, pioneered many of the tactics that made PB-4Y operations so effective against Japanese submarines and surface vessels. Operating from Henderson Field on Guadalcanal beginning in August 1943, Patterson's squadron flew missions that extended the boundaries of maritime patrol aviation far beyond previous operational limits. The PB-4Y1 carried specialized equipment that distinguished it from its Army Air Force's counterparts. SV radar installations provided surface vessel detection at ranges exceeding 20 miles, while sophisticated navigation equipment allowed precise position finding over the vast distances of Pacific operations. The aircraft's bomb bay could accommodate up to 6,000 pounds of ordnance, including depth charges, bombs, or the Mark 24 acoustic homing torpedo. Patterson's mission reports documented the effectiveness of PB-4Y operations against Japanese submarine traffic between major bases and forward operational areas. His squadron's first confirmed submarine kill occurred on September 12, 1943, when Lieutenant Thomas Chen detected a surface Japanese submarine 40 miles northeast of New Georgia. Chen's after-action report described the engagement in tactical detail that became standard for naval aviation. Target detected on ASV radar at range 14 miles, bearing 045 degrees. Approached from out of sun at altitude 500 feet. Submarine began crash dive at estimated range 2 miles. Dropped 4 Mark 17 depth charges in stick pattern. Observed 1 direct hit on submarine's pressure hull just aft of conning tower. Target sank immediately with no survivors observed. The Japanese submarine that Chun destroyed was I-20, a large fleet boat carrying supplies to the Japanese garrison on Bougainville. The loss of this submarine and its cargo represented exactly the type of interdiction mission that made PB-4Y operations so valuable to Allied strategy in the Pacific. Japanese submarines, originally designed for offensive operations against Allied shipping, had been pressed into service as cargo carriers because surface vessels could no longer penetrate Allied air and naval defenses. The technical specifications of Japanese fleet submarines revealed their vulnerability to air attack. The Type B boats, including I-20, displaced 2,584 tons surfaced and could achieve 23.6 knots on the surface. However, their large size made them easy targets for radar detection, while their slow dive time, approximately 60 seconds to clear the surface, provided ample opportunity for attacking aircraft to achieve weapon release. Commander Yoshiaki Oka, captain of I-35, experienced the deadly effectiveness of American maritime patrol aircraft during a supply run to the Japanese base at Truk in November 1943. His patrol report, recovered from Japanese naval archives after the war, described multiple encounters with PB-4Y aircraft that illustrated the impossibility of conducting submarine operations in areas under Allied air surveillance. Day 12 of patrol. American patrol aircraft contacts every 4 hours average during daylight operations. Forced to remain submerged during all daylight hours. Battery charge insufficient for high-speed submerged operations. Surface recharge time limited to night hours only. Mission schedule cannot be maintained under these conditions. I-35 was sunk by aircraft of VPB-102 on December 8, 1943, becoming one of 77 Japanese submarines lost to air attack during the Pacific War. The mathematical progression that had doomed German U-boats in the Atlantic applied equally to Japanese submarine operations in the Pacific. Radar-equipped aircraft made surface operations suicidal, while the need for battery charging forced submarines to surface, creating the conditions for their own destruction. The evolution of PB-4Y tactics included development of coordinated attacks involving multiple aircraft and surface vessels. Patrol Squadron 104, VPB-104, operating from the forward base at Los Negros in the Admiralty Islands, perfected techniques for submarine hunting that combined aircraft radar detection with coordinated attacks by surface destroyer escorts. Lieutenant Commander Robert Morrison, VPB-104's operations officer, developed the standard procedures for joint air-surface anti-submarine operations. His tactical manual, distributed to Pacific Fleet units in February 1944, outlined the communication protocols and attack coordination required for successful joint operations. Aircraft maintaining radar contact with submerged submarine reports position, course, and speed to coordinating destroyer. Surface vessel approaches from optimal attack angle while aircraft maintains surveillance. Submarine forced to remain submerged until battery exhaustion requires emergency surface. Aircraft and surface vessel coordinate final attack phase. These tactics proved devastatingly effective against Japanese submarines attempting to resupply isolated garrisons throughout the Pacific island chains. The Japanese Navy's decision to use submarines for cargo transport, forced by the elimination of surface supply routes, played directly into Allied strengths in anti-submarine warfare. The broader strategic impact of PB-4Y maritime patrol operations extended far beyond submarine destruction. These aircraft provided reconnaissance and surveillance coverage over millions of square miles of Pacific Ocean, creating an intelligence network that gave Allied commanders unprecedented awareness of Japanese naval movements. The radar-equipped aircraft could detect surface vessels at ranges exceeding 30 miles, providing early warning of Japanese naval operations and directing Allied surface forces to optimal intercept positions. Captain Ernest Chun, intelligence officer for Commander Air Force Pacific Fleet, analyzed the strategic impact of PB-4Y operations in a classified assessment submitted in June 1944. Maritime patrol aircraft have established Allied surveillance superiority throughout the Central and Southwest Pacific operational areas. Enemy surface vessel movements now detected immediately upon departure from major bases. Coordination with submarine and surface forces allows interdiction of approximately 75% of detected enemy movements. Japanese logistical capabilities reduced to levels insufficient for sustained defensive operations. The technical capabilities that made this surveillance network possible reflected the advanced engineering incorporated in PB-4Y aircraft. The ASV radar installations provided reliable detection of surface targets under all weather conditions, while improved navigation equipment allowed precise position reporting essential for coordinated operations. The aircraft's extraordinary endurance, up to 16 hours on patrol with auxiliary fuel tanks, created persistent surveillance coverage that Japanese forces found impossible to evade. Warrant Officer Hiroshi Tanaka, a reconnaissance pilot with the Imperial Japanese Navy's 902 Air Group, described the impossibility of conducting covert operations under Allied surveillance in his war diary from March 1944. American patrol aircraft maintained continuous coverage of all sea approaches to base. Surface vessel movements detected immediately. Submarine operations limited to night hours only. No possibility of surprise attack against Allied positions. Our forces operate under continuous observation. The psychological impact of constant surveillance proved as significant as the physical destruction inflicted by PB-4Y attacks. Japanese naval commanders found themselves unable to conduct operations without immediate Allied detection and response. The initiative had passed completely to Allied forces, who could choose when and where to engage while Japanese units reacted defensively to Allied movements. The rivalry between advocates of the Boeing B-17 Flying Fortress and the Consolidated B-24 Liberator extended far beyond mere technical specifications to encompass fundamental questions about bomber design philosophy, operational effectiveness, and strategic impact. The debate intensified during 1944 when the United States Army Air Forces conducted formal studies to determine which aircraft provided greater combat effectiveness per dollar invested and per aircrew trained. The statistical analysis compiled by the USAAF Operations Analysis Division in spring 1944 revealed significant differences in operational performance between the two bomber types. B-24 units achieved higher average bomb tonnages per mission due to the Liberator's superior payload capacity. 5,000 pounds standard bomb load compared to 4,000 pounds for the B-17. However, B-17 formations demonstrated higher bombing accuracy and lower abort rates, factors that partially offset the payload advantage. Colonel Curtis LeMay, commanding the 305th Bombardment Group equipped with B-17s, provided comparative analysis based on his operational experience in both the European and Pacific theaters. His classified report to 8th Air Force Headquarters documented specific performance differences observed during combat operations. B-17 formations maintain tighter defensive boxes due to aircraft's superior formation flying characteristics. B-24 formations exhibit greater spacing between individual aircraft, creating gaps in defensive coverage. B-17 crews report higher confidence levels in aircraft's ability to sustain battle damage and return to base. The technical specifications underlying these performance differences reflected fundamental design philosophies that influenced every aspect of bomber operations. The B-17's wing design emphasized stability and control at high altitudes, characteristics that facilitated precise formation flying but limited maximum speed and range. The B-24's Davis wing provided superior fuel efficiency and speed, but created handling difficulties that made formation flying more challenging. Major Harold Thompson, a B-24 pilot with the 93rd Bombardment Group, described these handling characteristics in a letter to his brother written after completing his combat tour in November 1943. The Liberator is a fast airplane and a long-range airplane, but it is not an easy airplane to fly. The controls are heavy at all speeds, and the aircraft requires constant attention to maintain level flight. Formation flying demands maximum concentration, especially during long missions when fatigue becomes a factor. The B-17 boys have an easier time staying in tight formation. Statistical analysis of combat losses supported Thompson's subjective assessment of aircraft vulnerabilities. B-24 units in the 8th Air Force sustained loss rates of 4.1% per mission during the period from January through June 1944, compared to 3.7% for B-17 units flying similar missions. However, the raw statistics failed to account for differences in mission assignments, with B-24s typically receiving longer range targets that involved greater exposure to enemy defenses. The analysis became more complex when survival rates were examined for aircrew members whose aircraft were shot down. B-17 crews had significantly higher survival rates in emergency situations. 62% of Flying Fortress crewmen survived aircraft loss compared to 47% for Liberator crews. This difference reflected both structural design factors and practical escape procedures. Captain Robert Mitchell, a flight surgeon with the 15th Air Force Medical Staff, studied aircraft survivability factors and identified specific design elements that influenced crew survival rates. His medical evaluation report, submitted in August 1944, documented the critical differences. B-17 emergency escape procedures benefit from aircraft's lower wing design, which facilitates bailout through bomb bay doors. B-24 shoulder-mounted wing design creates difficulties for crew movement within aircraft during emergency situations. Combat damage to B-24 top turret assembly frequently traps crew members in forward compartments. The water landing characteristics of both aircraft types revealed another significant difference in survival probability. B-17s demonstrated superior ditching characteristics due to their wing position and fuselage design, while B-24s tended to break apart rapidly during forced water landings. This factor proved particularly important in Pacific theater operations where long over-water flights increased the probability of emergency sea landings. Lieutenant Colonel James Doolittle, who had flown both aircraft types in combat operations, provided perhaps the most balanced assessment of their relative merits in his post-war analysis submitted to the Air Force Historical Division. The B-17 Flying Fortress was the superior combat aircraft for missions requiring precise formation flying, high-altitude operations, and maximum crew survivability. The B-24 Liberator was the superior aircraft for long-range missions, maximum bomb load delivery, and specialized roles requiring extended endurance. Each aircraft excelled in different operational scenarios. The production statistics that made the B-24 the most manufactured American military aircraft in history reflected economic and manufacturing considerations rather than pure combat effectiveness. Ford Motor Company's mass production techniques at Willow Run achieved manufacturing rates that Boeing's more traditional aircraft production methods could not match. The B-24's simpler construction facilitated rapid production, while the B-17's more complex design required skilled craftsmen and longer assembly times. Henry Kaiser's analysis of bomber production economics submitted to the War Production Board in July 1944, demonstrated the cost advantages of B-24 production. Liberator manufacturing cost per aircraft, $85,400 average including engines and equipment. Flying Fortress manufacturing cost per aircraft, $108,700 average. Production time per aircraft, B-24 47 days, B-17 63 days. Labor hours per aircraft, B-24 13,200 hours, B-17 18,900 hours. These economic factors proved decisive in determining production priorities during the period of maximum war production. American industrial capacity could produce more B-24s faster and cheaper than B-17s, providing the numerical superiority that ultimately proved more important than individual aircraft performance characteristics. The operational employment of both aircraft types demonstrated their complementary rather than competitive roles in Allied strategy. B-17s dominated strategic bombing missions over heavily defended European targets where precision, defensive capability, and high-altitude performance were paramount. B-24s excelled in long-range maritime patrol, Pacific theater operations, and specialized missions requiring maximum endurance and payload capacity. The United States Army Air Force's Strategic Bombing Survey, published in 1947, provided the most comprehensive analysis of B-24 Liberator effectiveness compiled by military authorities. Based on statistical analysis of over 40,000 combat missions and interviews with hundreds of aircrew members, the survey reached conclusions that would influence American military aviation doctrine for decades. The survey's findings on maritime patrol effectiveness confirmed the decisive role of radar-equipped B-24s in winning the Battle of the Atlantic. Allied anti-submarine forces equipped with these aircraft sank 93 German U-boats and contributed to the destruction of hundreds of additional submarines through coordinated attacks with surface vessels. The mathematical analysis demonstrated that maritime patrol aircraft achieved submarine detection rates 4 times higher than surface vessels operating independently. General Carl Spaatz, commanding general of the United States Army Air Forces, summarized the strategic impact of B-24 maritime operations in his final war report. Long-range patrol aircraft equipped with advanced radar systems eliminated the submarine threat to Allied shipping lanes. The closure of the mid-Atlantic gap by radar-equipped liberators marked the decisive turning point in the Battle of the Atlantic. German submarine forces never recovered from the losses sustained during the period of maximum Allied air coverage. The comparative analysis between B-24 and B-17 operations revealed significant differences in combat effectiveness that validated pre-war design decisions. The survey concluded that B-17s demonstrated superior performance in strategic bombing missions requiring precise formation flying and maximum defensive firepower, while B-24s excelled in long-range operations requiring extended endurance and payload capacity. Dr. Harold Urey, scientific director of the Operations Analysis Division, conducted statistical analysis of bomber effectiveness using mathematical methods developed specifically for military applications. His classified report documented the quantitative differences between aircraft types. B-24 units delivered average 8.7 tons of bombs per aircraft per month compared to 7.1 tons for B-17 units. However, B-17 formations achieved bombing accuracy superior to B-24s by factor of 1.3 to 1. Combat loss rates: B-24 4.1% per mission, B-17 3.7% per mission. The industrial lessons learned from B-24 production influenced American manufacturing doctrine throughout the Cold War period. The mass production techniques developed at Willow Run and other aircraft plants demonstrated the superiority of American industrial methods over German and Japanese manufacturing systems. The ability to produce advanced military equipment at unprecedented scale provided the United States with strategic advantages that extended far beyond individual weapons systems. The human cost of B-24 operations appeared in casualty statistics that reminded Americans of the price paid for victory. Of the 125,000 aircrew members who flew B-24s in combat operations, 26,000 were killed in action, wounded, or listed as missing. The survival rate for aircrew whose aircraft were shot down averaged 47%, lower than B-17 crews but reflecting the challenging operating environments where liberators typically served. Technical innovations developed for B-24 operations contributed to post-war aviation development in ways that extended far beyond military applications. The radar systems that made maritime patrol so effective became the foundation for commercial aviation navigation and weather detection systems. The long-range navigation techniques developed for Pacific operations influenced the development of intercontinental airline routes. The Davis wing design that gave the B-24 its extraordinary range and fuel efficiency influenced commercial aircraft development for decades after the war. The high aspect ratio wing configuration became standard for long-range transport aircraft, while the aerodynamic principles developed for the Liberator contributed to jet aircraft design during the 1950s and 60s. Captain James Mitchell, a former B-24 pilot who became a test pilot for commercial aircraft development, described the technical legacy in his memoir published in 1952. The flight characteristics I learned flying Liberators in the Pacific directly influenced my work on commercial transport design. The endurance requirements for 15-hour maritime patrols taught us about crew fatigue, fuel management, and navigation procedures that became standard for intercontinental airline operations. The strategic lessons derived from B-24 maritime operations influenced American naval doctrine throughout the Cold War period. The demonstrated effectiveness of land-based aircraft in anti-submarine warfare led to development of specialized patrol aircraft like the Lockheed P-3 Orion, which incorporated technological advances developed from wartime experience with radar-equipped Liberators. The statistical analysis of B-24 effectiveness provided quantitative validation for strategic bombing doctrine that would guide American military aviation development for the next 2 decades. The demonstrated ability of heavy bombers to operate effectively at intercontinental ranges influenced the development of strategic air command and the nuclear delivery systems that defined Cold War military strategy. Dr. William Mitchell, who served as statistical analyst for the Army Air Forces during the war and later, became Director of Operations Research for the newly created United States Air Force, summarized the broader implications of B-24 operations in his classified analysis, submitted to the Joint Chiefs of Staff in 1948. The Liberator program demonstrated American capability to design, manufacture, and deploy advanced military systems at scale and speed that exceeded all enemy capabilities. The technological and industrial lessons learned from this program provide the foundation for maintaining American strategic superiority in the post-war period. The economic legacy of B-24 production influenced American industrial policy throughout the Cold War era. The demonstrated effectiveness of government-sponsored research and development, combined with private sector manufacturing expertise, created the military-industrial complex that would dominate American defense spending for the next 4 decades. The Willow Run facility itself became a symbol of American industrial capability that continued operating in various capacities throughout the post-war period. Ford Motor Company converted portions of the plant to automobile production, while other sections housed research and development facilities for advanced aircraft systems. The training methods developed for wartime aircraft workers influenced industrial education programs that prepared American workers for the technological challenges of the Cold War period. The international implications of B-24 effectiveness extended beyond immediate military applications to encompass broader questions of industrial capacity and technological development. The demonstrated American ability to produce advanced military equipment in quantities that exceeded Axis production provided strategic advantages that influenced post-war diplomatic and military relationships. Allied nations that received B-24s through Lend-Lease programs gained operational experience with advanced American technology that influenced their own post-war military development. The Royal Air Force operated over 2,000 Liberators during the war, while the Royal Canadian Air Force received 1,200 aircraft that formed the backbone of Canadian maritime patrol capabilities well into the 1950s. The final assessment of B-24 Liberator effectiveness must acknowledge both the aircraft's decisive contributions to Allied victory and the human sacrifice required to achieve those results. The 93 U-boats sunk by Liberator crews represented victories that helped save thousands of Allied merchant seamen, while the closure of the Mid-Atlantic Gap ensured the survival of convoy routes that sustained Britain throughout the darkest period of the war. The 18,482 B-24s produced during World War II represented more than statistical achievements in mass production. Each aircraft embodied the technical skill, industrial capacity, and human dedication that enabled democratic societies to defeat totalitarian regimes through superior organization and technological innovation. The Liberator's legacy encompasses not only its direct military contributions but also its demonstration of American industrial democracy's capacity to mobilize resources and achieve objectives that seemed impossible at the war's beginning. The story of the B-24 Liberator in maritime strike and bombing operations illustrates the decisive importance of technological innovation, industrial capacity, and human courage in determining the outcome of modern warfare. From the engineering brilliance of the Davis Wing to the mass production miracle at Willow Run, from the radar breakthroughs that made submarine hunting possible to the individual heroism of aircrew who flew dangerous missions over hostile oceans, the Liberator program represented the best qualities of American democracy applied to the challenges of global warfare. The statistical record 93 U-boats sunk, the mid-Atlantic gap closed, 18,482 aircraft produced, tells only part of the story. The complete narrative encompasses the transformation of American society and industry, the development of technologies that would shape the post-war world, and the demonstration of democratic values under the extreme pressures of total war. The B-24 Liberator stands as both a remarkable military aircraft and a symbol of the industrial democracy that proved capable of achieving victory against seemingly insurmountable odds.